Thank you, Ryan, for the introduction, and thanks for the invitation to speak here. Indeed, today I would like to talk about negative dependence and machine learning, and that's a topic where very recently there's been a lot of very interesting developments that I think are good to know, and I would like to introduce you to these a little bit. So let's first start with some settings. So what do I mean when I talk about negative dependence? And in fact, it can mean various things. So first of all, I'll talk only about discrete distributions. That means we have n binary random variables, or equivalently, we have a universe of n items, and we randomly observe subsets of these items. That's an equivalent thing. So what could these be? For example, you could see that there's a user, and this random subset is what does this user buy on a given day. So for example, we could have these items, and now you observe that the user buys a book and a phone and a cab, for example. Maybe not today, this particular hat, but in general. So now there could be dependencies between certain items occurring together. For example, if the user buys a phone, it's unlikely they buy two phones on the same day. So this is essentially what I here mean with a very weak notion of negative dependence is essentially pairwise negative correlations, that the probability of observing these two items together jointly is smaller than if they were independently sampled. So I can rearrange this inequality a little bit, and I see that basically conditioned on knowing that the user has bought the blue phone, it's less likely to observe that the user also buys the green phone. So that's negative correlations. Now, this topic of negative dependence has recently gained a lot of interest in machine learning, so there has been workshops, a tutorial, and there's actually a book, also a very nice book, very related to the topic. And there's been several papers that's just sort of in the background here at UAI, at NeurIPS, at ICML, talking broadly about the concept of negative dependence. So why is negative dependence so interesting, and where does it come up? So the first thing that's maybe the simplest is actually sampling without replacement. So you have n items, you choose k randomly without replacement. That's a negatively dependent distribution. And that's if you run SGD, that's essentially what you do if you do SGD sampling without replacement. So that's one major thing that we are doing. But there's much more. In particular, if you think about what can these things actually express? What can you express with negative dependence? Well, given that I know a certain item is observed, other items become less likely to be observed. So essentially, that's a notion of repulsion that I can model here with this inequality. So I can model repulsion. Now, if this repulsion is actually dependent on how similar are these items, I can model things like diversity. I want to sample a subset of items that is diverse. And that is something that is of great use in many different applications. So let me just mention a few of those without going into details. So one of them is actually in probabilistic modeling. If you want to put negative dependence in your priors, for example, that's where it comes up. So one application of this is recommendation. There have been several works where people have used negatively dependent distributions to model essentially that you don't want to show redundant things to a user, so you actually want to sort of capture better the span of interests. So the most recent paper possibly on this is a paper by Google on using a certain distribution on YouTube for recommendation, but there's many other works like that. So that's one thing. So we can model diversity. This diversity actually can have other implications too. So for example, for interpretability. If you think about describing your data with clusters or features, and you put a prior that these should be really, really different from each other, that can actually make them a crisper description of your data. Because they are really different, maybe they're better interpretable as certain groups of data points. And that's another application where you can use negative dependence in probabilistic modeling. And there's many more. There's actually nice other work, also from Ryan's group, for example, and modeling, for example, firing of neurons, modeling other things that have negative dependence, or basically repulsion in the observations. But so probabilistic modeling is one side where this is very useful. There's other areas that are useful for machine learning where this comes up. And another one is randomized algorithms, where you especially care about the sampling part. So we are probably all familiar with the problem that we have large data sets, large models, we want to somehow compress them. And one way to compress them is to take this large thing and sample a random subset of that, however you define that, and that is actually going to give you a summary of it. So one area of this is matrix approximations that has received a lot of attention too, randomized numerical algebra, linear algebra. So we have a large matrix, for example, a kernel matrix. We would like a low-rank approximation of this. One way to obtain this is to sample columns from this matrix and then construct the low-rank approximation from that. You can use similar ideas actually to prune down neural networks. If you have a large neural network, you want to just retain a few of the units and throw out the other ones. How do you do it? You ideally want to throw out the redundant ones. So if you keep a diverse subset, you make sure that you don't actually keep redundant ones. And you sort of, the little budget that you have, you actually use it very wisely. So once again, you can use diversity and negative dependence to sample units from a neural network to prune it down. And finally, there's been a lot of work in sparsifying graphs. And a lot of this work relies on retaining properties of the Laplacian of the graph. And that's, again, where actually a lot of the things that I'm talking about are very related to these kinds of ideas of sparsifying networks, sparsifying graphs by retaining some spectral structure of these. And here it's not so obvious to see the negative dependence, but you can think about if you have sort of two clusters and lots of edges in parallel, you'll sample only one of them. That's where the negative dependence, for example, comes in. And then there's many more applications. If you just broadly think about sampling diverse subsets, getting good summaries, essentially every area where you need to do exploration, such as search, Bayesian optimization, experimental design, exploration, for example, in reinforcement learning. These are all areas where people have explored distributions of with negative dependencies to basically explore the space that you have as well as possible. So you have this kind of repulsion property. Now, one specific family of distributions that has been used a lot in these applications, and is probably the most well-known in machine learning after sampling without replacement, is called determinantal point processes. And some of you probably have heard of these. So the idea is very simple in pictures, and it actually captures the notion of diversity very, very pictorially and nicely. So let's say that you have this universe of items, and each item is described by a feature vector. Now the probability of observing two items together, jointly, is proportional to the volume that is spanned by these feature vectors. So you see essentially if the vectors are very orthogonal, this volume is going to be very large. If the vectors are very close to each other, essentially almost collinear, then this volume is going to be very small. So the probability of seeing two things that are very close together is actually very, very small. So this is one way to capture actually this notion of diversity. And you can now generalize this from 2 dimensions, as I have here, to multiple dimensions, where you get, instead of just planes, you get cubes, etc. So this is, of course, a nice picture, but it's better described in some more mathematical closed forms, and that is via determinants of matrices. So the same volume that I have here can be just written down as a determinant, where you take the inner product matrix of your feature vectors, or just a similarity or kernel matrix, and then the probability of observing a certain subset is computed as follows. So let's say I want the subset 2, 3, 4. I just take the rows and columns 2, 3, 4 indexed in this matrix. That gives me a little submatrix, and then I take the determinant of that. That's why they're called determinantal point processes. And now they have lots of nice properties. For example, normalization constants, so there's partition functions, marginals, conditioning, all of this is very easy and closed form with these kinds of processes. So they're actually very, very simple to compute with if you can do large matrix computations. They're also very easy to define, because all we really need to define is a similarity matrix or feature vectors. So that's very nice. But there's much more to negative dependence, and I would like to expand a little bit more on this. This was just to show you that there's a lot of relevance and interest in machine learning. And I would like to do this by taking ideas from machine learning and sort of merging them with ideas that have recently appeared in mathematics, in particular in algebraic geometry and algorithms, and sort of show you what kinds of implications they can have. And to sort of summarize what you'll see in this talk, let me just show you this picture. If you have negative dependence, in many cases there's very nice implications computationally. So for example, you get concentration of measure inequalities, which otherwise is kind of hard with variables that are not independent. You can get fast sampling algorithms, provably so. You can actually get other implications for randomized approximation algorithms, and you get guaranteed approximation factors for partition functions, marginals, and so on. So these are all things that are potentially super interesting to know and to explore and to exploit in particular. I don't have time to go through all of these 4 boxes here, so I'm going to focus on sampling because this is important both for probabilistic inference and also for randomized algorithms. So now, negative dependence, as I stated this, is in most cases too weak to have all these nice strong implications. So we need something stronger than that, essentially strengthen our pairwise negative correlations to something stronger, such as higher order. And so essentially what we need is strong notions of negative dependence. And I'm going to tell you a little bit what kinds of notions these could be. So that's roughly the big picture that could be potentially useful. We're going to talk mostly about sampling today. So what are these strong notions of negative dependence? So now I'm going to show you a bunch of terms, and during the talk I'll explain what they mean. So here's a picture. These are the notions of negative dependence we look at. The first one is called strongly Rayleigh. So that's sort of the strongest that has all these implications. And then we're going to relax it in different ways. And you can think of these relaxations as follows, that all of this negative dependence actually inherently has a lot to do with concavity. So the right-hand side, log-submodularity, is essentially a notion of discrete concavity. The left-hand side is related to some continuous notions of concavity, strong notions of concavity. The left 2 points are related to the theory of polynomials and algebra. So that's roughly how you can think about this picture, and don't worry about the exact terms right now. So let's start with the center, sort of the strongest notion, and one of the best studied ones. And this actually, one part of this started with sort of that there was a lot of notions of negative dependence out there that had nice implications, but also some weaknesses. For example, if you took conditional or marginals, that suddenly this condition doesn't hold anymore. So in 2000, the probabilist Robin Pimentel wrote a paper towards the theory of negative dependence, where he really summarized all of this plethora of different conditions and said that what would be sort of a good, strong notion of negative dependence that captures a lot of what people have been thinking about, and also it has nice closeness properties. For example, if your distribution has this negative dependence property, you take marginals of this distribution, it still has these properties, they don't break. Or you do conditioning and it still holds. So can we have something like that? And it wasn't clear at this moment that this actually, what this should be. And there's an interesting fact to that, that negative dependence in that sense, it's much more tricky than positive dependence, perhaps surprisingly so. So now, over the years, actually, there has been answers to this question, and many of these actually relate to a certain type of polynomial. So the key sort of to unifying this picture lay in the so-called generating polynomial. So what is this generating polynomial of my distribution? So basically, if I have n items in my universe, I have n variables as arguments to my polynomials. I call them z1 to zn, one for each item. And these are complex variables. Now, this polynomial has a term for every subset that I could observe. The coefficient for this term is just the probability of that subset. And then I just take all the coefficients that correspond to that subset and take their product. So you could also think of this as an expectation. This is called the generating polynomial. And to make you sort of a bit more familiar with this, let me just show you one concrete example. Let's say we had 2 items. So there's basically only 4 outcomes we could have. Sampling nothing, sampling number 1, sampling number 2, or sampling both of them. So that corresponds to the 4 terms in my polynomial. And now I just wrote mu1, 2 to have the probability of item 1 and 2 jointly together. So why is it useful to look at the length of these polynomials? Like, it's just another way to write my distribution, and there's actually a one-to-one mapping between these polynomials and distributions I could have. Now, the interesting thing is that operations on my polynomial, because I have this one-to-one mapping, directly correspond to operations on my distribution. And likewise, properties of my polynomial could tell me properties of my distribution and vice versa. So this could be potentially very useful, especially if these are polynomials that are well studied. So to just show you, like give you an idea of one simple example, let's say we wanted just the coefficient of Z1. That means what's the probability of observing just item 1. And one way you can pull out that coefficient is to take derivatives. So you take derivative with respect to Z1, and you set all the arguments to 0. That's going to pull out the first coefficient. So many of these operations are just taking derivatives, setting arguments equal, setting arguments to certain values, etc., etc. You can do more complex things, but that's one of them. So that just to give you an idea that sort of operations on the polynomial directly correspond to operations on your distribution. So as I said, now actually properties of the polynomial potentially tell us about properties of the distribution. So one way we can define a class of distributions is to define this via a class of polynomials corresponding to these distributions. And one way this has been done, and this has, yeah, okay, there has been.
So what does Z represent here? Because there is no Z on the right-hand side. So it's only Z1, Z2.
Oh, Z is the vector of, sorry, okay, yeah, so Z is the vector of Z1 to Zn. Yeah. Yes?
Why would you want the Z to be in the complex element rather than real?
Yeah, that's a very good question. It's going to become clear on the next slide why you need this to be complex. You could, that's true, you could here define it also to be real, but to actually get the definition I want to get at, you need the complex numbers. So this definition that I'm going to go to answered lots of these questions by Pimentel, and it essentially defines a class of distributions via a class of polynomials. So we again look at the generating polynomial, and the way you define this class is, it looks a bit scary at first looks, I'm going to explain it, where are the zeros of this polynomial. So 0 of the polynomial means which arguments make it 0, so which zi's make it 0. And now there's this notion in mathematics of stability. It basically means there's some region in your space where the polynomial doesn't become 0. So real stable in this case, it's essentially a generalization of having only real roots. So that means it shouldn't have zeros in the complex plane, and that is if you actually had only one argument in this polynomial, or you set all the zi's to the same z. In that case, what this condition here means is that the polynomial only has real roots, meaning only real numbers can make it 0. In the multivariate case, this is a little bit more complex. Essentially, it generalizes to if all the arguments have positive complex part, then the polynomial shouldn't be 0. So these are called real stable polynomials. If my distribution has such a generating polynomial, it turns out to have very strong and nice negative dependence conditions. So this was shown in a paper by Borsia, Brandon, and Liggett in 2009, where they basically answered a lot of the questions that were raised in this earlier survey paper by Pimentel. So this class of distribution sort of was one way to answer a lot of these questions. So now why is this also particularly useful? Real stable polynomials are very well studied in mathematics. We know what kinds of operations we can do on the polynomial and still retain this property. And all of these operations actually correspond to operations on my distributions that are going to give me some new distribution. And an example of this is conditioning and marginalization. Among several others, we will see one more example. So again, what are examples of this kind of condition? It looks kind of not so easy to see what kind of distributions would have it. One is sampling without replacement. The other one is actually our familiar determinantal point processes. So the example I showed with the determinants and these parallelograms earlier on. So in this case, this crazy looking generating polynomial actually is very close to the so-called characteristic polynomial of the matrix. If you remember your linear algebra, you use that thing to compute the eigenvalues of the matrix. So now that means actually that the roots of that polynomial correspond essentially to the eigenvalues of this kernel matrix. And since it's a PSD matrix, we know that the eigenvalues are real and positive, non-negative essentially. So this actually has this strong Rayleigh property. So that notion of strong negativity, even though it's not so obvious, is actually very powerful. And I could essentially go and take my initial picture and replace the inner part by strongly Rayleigh distributions. And I get all these nice implications that I had promised earlier on. And I just put a few of the references here. There's several others. That's a very active area of research. And it has been exploited a lot in theoretical computer science, less so in machine learning, but I think there's lots more to do. So as I said, let's look at one algorithmic implication, and that is sampling. So how do you sample from such measures? For the special case of DPPs, or determinantal point processes, there's actually an elegant way to do this, which goes via an eigendecomposition of the matrix, where you essentially sample eigenvalues and then sample according to that. That is super nice, but it really relies on the matrix properties, so you don't have it for the general class of strong Rayleigh measures. And also in some cases this can become expensive because it needs an SVD, so there has been lots of work on improving on this because of that big matrix that you have to compute and do computations with it. So what about the general case? So what can we do in the general case? We could try MCMC. Now MCMC is usually not known as like an easy method to show that this actually converges, like I run it and I don't know when to stop, and especially provably so. But it's a method that generally you can derive, and in many cases it's going to get you eventually there. So what would MCMC look like for these kinds of distributions? We have this random subset, so essentially it's a very simple chain you can run. So you start with a subset, and then you randomly sample one item inside and one item outside the set, and then you either remove A, you add B, or you do both, or you do nothing with the appropriate probabilities. So that's super easy to implement. It has the advantage for the special case of the DPPs that you never ever actually need to compute that huge kernel matrix. You only can compute with much smaller matrices. Now the key question is, how often do I need to do this? How many iterations do I need to run to actually converge to a sample that's a good sample from my distribution? Let me first answer this question empirically. So here's one empirical example where it's not a super accurate measure of convergence, but essentially this is for a matrix approximation problem where the y-axis is the matrix approximation error. But it sort of gives us an idea, like in an application, how would this perform. And you see actually very quickly it sort of stabilizes to a low value and it's basically there. So empirically it seems to actually converge fairly quickly. So is this something that I can actually formalize because I promised fast sampling algorithms, and this is just an empirical example, one example. So what do we do in theory? In theory, the quantity that we're interested in is called the mixing time. So what is the mixing time? Essentially, I look at the iterations of my sampler, and in each iteration I get a distribution where basically for each set, how likely is it that I've reached it? And I just look at like how close is this distribution to the actual distribution that I'm interested in. And if they're close enough, then I have a good sample. And now I look basically if this should be closer than smaller than epsilon, how many iterations do I need? So this is like a convergence analysis. So what are the results for that? And actually the first results are older than the strong Rayleigh paper. They are for a special class in combinatorics, so-called balanced matroids. And after that, there were generalizations that used actually more of the theory of the polynomials also. So the first results on this were for the case, it's called K-homogeneous here. Homogeneous means basically that you only observe sets of a certain cardinality. So you actually condition on the fact that you're sampling only a set of size K, but you have these strong Rayleigh properties. So in this case, actually, you can show that essentially you need nk steps. So n is the number of items in my universe, k is the number of items you observe. For the general case, when you don't condition on cardinality, it was open, and we closed that gap by showing that if you have a sampler for the fixed cardinality case, you can always extend it to a sampler for arbitrary cardinality. So for general strong Rayleigh distribution, so basically going from a, if you take the case of a DPP, going from a DPP that can only sample of size k to arbitrary numbers of items. After that, especially last year and this year, there have been various improvements to these bounds. And what they essentially did is they replaced the log by a double log, and perhaps more importantly, they removed the n. So that means actually the running time is basically almost linear in the number of items that you sample. So this is for a fixed cardinality again. And it doesn't actually have the n even in there anymore. So up there, what I replaced for the general case is replace essentially the k by n. So that is potentially very useful because these bounds are fairly good in terms of sampling, in particular if each step in your sampler is relatively cheap. So these are provable now guarantees on the convergence of these chains for all strong Rayleigh distributions. I won't go into detail on how you actually prove these. What I would like to show you is how do you get from the fixed cardinality case to the general case, because that's easy to show in pictures and it actually uses the relation to the polynomials again. So what do we have? We have our universe of n items, and we have a distribution over subsets of these items of any cardinality. What I can do is if I condition on a certain size, I can sample from that. So what I'll actually do now is I will reduce the general case to the fixed case as follows. I just duplicate my n items, and now I sample n out of 2n. And out of these n that I'm sampling, I'm only looking actually at the one that fall into the first part. And obviously, n out of 2n between 0 and n can fall into the first part, so I'll get any kind of cardinality. So that works, and I can sample n out of 2n if I find a way to get a joint distribution over these two parts whose marginals actually exactly correspond to the distribution that I'm interested in, first, and second, that still has this strong Rayleigh property that I need to guarantee that I can sample fast. So that's the criterion. How do I do this? In fact, it's actually, once you see it, it's not that hard, but you have to see it, and the proof that it has the strong Rayleigh property now relies on the polynomial. So how do I do it? Essentially, I say if I have 3 in the front, I just take a uniform distribution over all possible completions on the second half and distribute the mass. So that's how I do it. Does this have the strong Rayleigh property? Not so obvious because it goes via these zeros of polynomials and so on. Now I have this larger polynomial, how to prove that. In fact, the key insight is if I do the same operation on my polynomials, there is an equivalent operation exactly on these polynomials, which is called symmetric homogenization, and that is actually known that the real stable polynomials are closed under that. That means from the mass of these polynomials, I know that this generating polynomial of this distribution actually has the property that I need. So the theory of polynomials actually really helps me here. So we have these fast samplers now. What are implications of these? So let's look at a few implications of having these samplers. What does it mean for us? So one implication is in approximating matrices. So that example I showed earlier on, you want to approximate this large matrix. One way to do this is via the so-called Nystrom method. We select columns from the matrix, then we just take an outer product of these columns and normalize it, and that gives me an approximation. Now obviously, the quality of this approximation heavily depends on which columns I choose. And hence there has been a lot of work on choosing these columns. Well, if you think now, the distribution I showed you earlier, these determinantal point processes, what they do is they actually sample vectors that are almost orthogonal. If you think about what kinds of columns you would like to sample in this case, you would like to sample columns that span sort of all the space of the columns of your matrix very well. So that seems like a natural distribution to capture that span of the columns of the matrix. So we could sample them from a DPP with a constraint on the cardinality. And indeed, if you do this, you get reasonable actually approximation bounds both for the matrix approximations and actually if you say this is a kernel matrix, you do kernel learning for the risk if you actually do learning with it. And I won't go into detail about these bounds. One thing that this depends on is how well can your matrix at all be approximated by a low rank matrix. So this last term back here with the e's, that essentially is some way to measure like how the spectrum of the matrix decays. What does this look like empirically? So theoretically, I do get approximation bounds. What about empirics? So here is an example, a result where I plot time and error. So basically the time to select the columns and the error, the approximation error you get. And this looks fairly similar for both the risk and actually the matrix approximation. And what you see is, so what I put in a circle here is the green points are the ones sampled from a determinantal point process, and the other ones are other methods that have been used in the literature. And you see actually empirically also it works fairly well. And it is relatively fast because we actually used MCMC to sample from those. This can be further accelerated by using ideas of lazy sampling and lazy computations because you still have to compute determinants in each step. By using ideas from quadrature and basically lazy computations, it's still exact, but you can potentially save a lot of computation if you have sparse matrices. So this was implication number 1. We can use it for randomized algorithms for sketching. Implication number 2 is for experimental design. So in this case, I have a very long and fat matrix, which has many, many more columns than rows. And each of the columns corresponds to a potential experimental setting or say a data point where I could measure a feature label. Now I want to learn, say, a regression model on this. So I want to sample, because it's regression, I want to sample at least as many columns as I have rows, a few more, maybe, but I want to sample them wisely. And there's actually this entire area of experimental design on measuring like basically the uncertainty of your estimator that results from it, and then addressing like how could you potentially minimize that uncertainty. So choosing the ideal set of columns is actually NP hard. We cannot do it, but we can approximate it. And one result for approximating this is a paper by Avron and Boutsidis in 2013, where they showed that for certain of these experimental design criteria, you would actually get guaranteed approximation bounds if you would sample them from a certain distribution. So they just specified the distribution. The distribution is also known as volume or dual volume sampling. Essentially, it also has a determinant, but the difference to a determinantal point process is that the determinantal point process would correspond to the inner product of the columns. This thing is the outer product of the columns. DPP could not sample actually more columns than rows because the matrix would be low rank and we have zero determinant. But they did not actually specify how you can sample. They just said if you had this distribution and you could sample from it, you get this approximation result. So now it turns out actually this distribution has the strong Rayleigh property I talked about. So directly as a corollary, you get that you actually can do fast sampling. And you get now actual algorithms for getting these approximations. You can also de-randomize it if you prefer a deterministic version. But essentially, this shows that you can actually sample from these measures. Now, let's look at a different example, and let's think about what happens if we take negative dependence to the extreme. So here, what I have is a set of points, and I have a distribution with strong negative dependence, and the color of the points is how often they were sampled when I do repeated sampling. What you actually see is that the points to the outer rim of our point cloud here, they actually get sampled more often, obviously because we have repulsion. So these are actually the outliers. So now if I had a way to take my negative dependence to the extreme, I could actually have an anomaly or outlier detection method based on these negative dependencies. How could I do that? Essentially, I would need a way that if I have negative dependence, if I make it more and more negatively dependent, I basically go towards the outliers, and that actually is a reasonable method to do outlier detection. You get very competitive results with that. So how could I do this? One way to do this is to use essentially a temperature parameter, where we take a strong Rayleigh distribution and we raise it to some power p. If p is 0, you get a uniform distribution. If p is 1, you get the original distribution out. If p is smaller than 1, you get something in between that has lower negative dependence. If p is bigger than 1, you get something that has higher negative dependence. So can I still sample from that? Unfortunately, it is not the case that for all possible p, this distribution retains these nice strong Rayleigh properties. However, in many cases, it's still close enough. You can actually use the strong Rayleigh distributions to well approximate it in a sampler. Or you can go and look at more general classes of negative dependence that possibly capture this. So let's look at that. So let's look at some generalizations of these strong Rayleigh measures that actually capture, for example, this distribution among others. So I want to first look at the discrete case, and that is the concept of submodularity, which itself has actually been looked at quite a bit with relation to machine learning, but a bit less so with relation to probability. So in this case, I actually look at the logarithm of my measure. So I can say that mu of s, my probability, is just proportional to e to the f of s for some set function f of s. This set function has the submodularity property if it has so-called diminishing returns. That means basically that I look at the so-called marginal gains. I basically look at if I have a set S, say I have this hat, and I add one more item to the set, how much does my function increase? So let's say that's the value of having this joint set of items if I add the phone to the hat. Now, as I have already more and more items, this marginal gain of my phone can only decrease. It can never increase. So that's the property of decreasing marginal gains. You can think of this also actually as a discrete derivative, the marginal gain. It's basically the two function values. So what this really means is that my derivatives are shrinking, and hence the sort of relation to discrete concavity. So if my distribution has this property in the logarithm, then I say it's log-submodular. How is this related to negative dependence? You can see it also captures maybe some sort of repulsion or diversity if I maximize it. I actually can also write it this way. So if I take basically exponentiate this inequality and rearrange it, I get something like this that looks actually a little bit like conditionals. It's not exactly that, but it looks a little bit closer to that. So what are examples of log-submodular distributions that people have actually used? One is this exponentiated strong Rayleigh measures that you can use, for example, for outlier detection, for several other things. Another one is so-called facility location models for summarization and compression, where the red stars here are the points that I'm sampling, and essentially their score or probability depends on how well do they capture the entire data set, basically a measure for each blue point, how close is it to any point that I've sampled. So why is submodularity a good property? It's in some sense much weaker than the strong Rayleigh property, but we actually know a lot about optimizing submodular functions. In particular, if you want to maximize a submodular function, I know that fairly simple, greedy algorithms actually work provably well. So they don't get the optimum, but they get a guaranteed approximation. And that would basically give me a mode finding thing. So that would give me a way to find a mode of my distribution. But actually, these optimization results have many other implications. For example, I can use ideas from optimization to do variational inference with log-submodular distributions, get actually guaranteed approximations to my partition functions also, and I can also accelerate sampling. since I'm talking about sampling today, let me talk about the second part. Essentially, the idea is to use ideas from optimization to accelerate sampling, which in the continuous world actually has been explored quite a bit. So why can potentially sampling be slow if I do MCMC? Well, essentially I could have, if I look at the state space, essentially the space of all possible sets that I could sample, there could be a mode here and a mode here, and going from one mode to the other is actually, there's a low probability region, so basically there's a bottleneck. It's very hard to get from one side to the other, so it's very hard to reach the other side if you're on one side. And to accelerate the sampler, what we need to do is we essentially need to be able to jump between these regions better, more quickly. How can we jump between these regions? We actually need a good direction to jump into. And one way to get this is by a gradient information of my distribution. And in this case, what I can get is subgradient. So I can actually get subgradient information and use this to guide my sampler to jump to certain areas. What is a subgradient for a set function? In this case, essentially, it's just essentially a weight for each item. So a weight for each item is like a product distribution. This actually is very related to optimization 2 and greedy algorithms more than you may think. For example, many of these greedy algorithms can essentially be viewed as computing a specific subgradient and just choosing the k items with the largest weights in the subgradient. So essentially here, this is a probabilistic version of such a greedy algorithm. Now the way we actually use this is that we take the subgradients, each of them corresponds to a product distribution, and we take mixtures of these and use this as proposals in an MCMC. So does this actually lead to speedups? Is this something that's useful? We have partial theoretical results saying that in special cases you actually provably get an exponential speedup. In the general case, let me just show you one example, empirical result. So here's the time that it takes, and on the y-axis we have some measure of convergence of the chain. And the blue line is essentially what you get with a standard method, standard Gibbs sampling. The other two lines are what you get if you do this acceleration. So you do actually see improvements in practice too from doing this kind of jumps with subgradients. And the way we do these jumps is actually we do them occasionally, so we mix it with the actual Gibbs sampler. So here the message is that if I have log-submodular distributions, that's a weaker condition, but since we know a lot about submodular optimization, I can use the ideas from submodular optimization to still help me do sampling and other things I'm interested in for probabilistic inference. So now, in the remaining time, let's look at another property, and that is something that has recently gained a lot of attention, in particular in the last part of last year, and that is strong log concavity. So the way this connects to the other things I've been talking about, the center part talked about polynomials and algebraic conditions. So this is also going to be an algebraic condition. The second part talked about essentially a notion of concavity, of discrete concavity for set functions. And we saw that this is highly related to negative dependence and actually gets us accelerations because I know a lot about gradients, etc. So this is going to be related both to concavity and to polynomials. And you already see from the name, it's called strong log concavity. So here again, we go back to our polynomial, our generating polynomial. Let me remind you, we have n items in my universe, one variable zi for each item, and a term for each set that I could sample. The probability is the coefficient. So now, while previously we looked at where are the zeros of this polynomial, now we just look at, is this polynomial concave? But I relaxed the concavity a bit. I want it to be log concave. So I take the log of this q, and I say it should be concave in z. And not only that, I want all the derivatives also to be log concave, unless they are 0. So that's my condition. This is actually still somewhat related to zeros because in the Hessian it basically means that you have at most one positive eigenvalue. So what are examples of these strongly log concave distributions? First of all, it's a generalization of the strong Rayleigh measures I talked about earlier, so any of these also satisfies the strong log concavity. Powers of these, for powers between 0 and 1, satisfy this condition. And several other distributions. So the most recent results actually looked at certain classes of combinatorial objects called matroids and basically uniform distributions over these combinatorial objects, which answer the long-standing questions whether you can sample from them efficiently, and you can actually. There's potentially many other examples that are not in here and that are still to be explored. So what are the implications of this strong log concavity? Why is this potentially useful? It is a weaker condition, but it still retains some of the strong implications that we are so happy about. For example, in fact, the first time they were studied in 2009 by Leonid Gurwitz was with the motivation of approximating a partition function. So you do still get approximations of partition functions with guaranteed factors, approximation factors, and actually the best ones to date for these kinds of distributions. What you also get is fast sampling algorithms. So in fact, the bounds that I showed you, these like k times double log, etc., they also hold for this class of distributions. So you still get fast sampling for the restriction of a certain cardinality. So again, like the cardinality restricted, I can only sample sets of a certain size. I condition on that. So these are the strong strengths of these. In some senses, they are weaker than some of the conditions I've talked about earlier. So for example, what we had for the strong Rayleigh measures, that we had this fairly intuitive proof of going from a fixed cardinality to a general sampler. What about general sampling for these kinds of distributions, if I go beyond the fixed cardinality? In fact, the way I extended the sampler is no longer possible the way I showed you, because the closeness properties of this class of polynomials are weaker than for the real stable polynomials. However, you can actually get a modified version of this thing, which is an approximation, but you can still use that for sampling. So you need to do a little more work here. The other thing I talked about was submodularity. So we had that diminishing returns property, and strong Rayleigh measures satisfy this diminishing returns property. The log concave measures do not satisfy it exactly, but approximately. So you get a weaker version of this. Essentially what you have to do is you have to add this minus constant here. So you get this inequality up to a constant. You can still use that to get approximations and basically get approximations with greedy algorithms, but it's not exact. So these are the two ways that it's somewhat weaker than the previous conditions we had, but you see it's still sort of very closely related. So like approximate version of this homogenization thing I did, approximate version of the diminishing returns when you can get approximate versions of the optimization results. So that's the last one. This class of distributions has recently gained a lot of attention because it's actually using this strong log concavity property. Several open questions were answered in theoretical computer science and mathematics. There's a lot, I think, to be explored for machine learning too here. So with that, let me just go back to one of the first slides I had. What we saw was that there's like basically 3 different notions of strong negativity that I talked about. With many of them, you get implications that are super interesting, such as fast sampling algorithms. Apart from these fast sampling algorithms, you also get concentration of measure inequalities. You get approximations for partition functions, and you do get approximation algorithms of various kinds. I showed you a few of them. You get various others, such as approximations for traveling salesmen, approximations for many graph algorithms, and so on. And the thing to be explored here is really this landscape of these strong negative dependence conditions, which are, as I said, a bit more complex than positive dependence. But they still now like we have a better characterization and better understanding of what they could be. These together imply a lot of the properties that we may be interested in, and that people in the past have just had sort of partial conditions, like here, if I have this thing holding, I can do this. If I have this thing holding, I can do this, and so on. That gives us many, many applications. There's many more than these. I talked about some of them that we could be interested in, mostly probabilistic modeling, randomized algorithms, and so on. You may still ask the question, what if my distribution does not exactly have one of these properties? So what you can still exploit is if your distribution is close enough to one of these, by, for example, doing variational inference, by using some of these as the approximation distribution, or to do sampling and use one of these as the proposal distribution, because you can do fast sampling with them. That also can be done. It has been done in a few cases. That's something to keep in mind if you have a distribution that you want to reason with. With that, let me just thank my co-authors and collaborators on several of these works, and thank you for your attention.